purpose of practicing all those derivatives is because today I needed you to have derivatives fresh in your mind because we're going to learn the antiderivatives. Okay, math is always about learning things forward and learning things backwards. The first kind of math you learn when you're little is adding. But then what's the next kind of math you learn?
Subtraction.
Which is just adding backwards. Okay, then you learn multiplying when you get to like second or third grade, and then what do you learn? Dividing, which is just multiplying backwards. Okay, then you learn how to square. And they teach you, what does a square mean or a cube? But then what do they teach you after that? Square root, which is doing it backwards. Everything is always learning it forwards and learning it backwards. So in a calculus class, you learn all the derivatives first, and then you learn all the derivatives backwards, which is antiderivatives. So this is like calculus 2. It's the beginning of a second semester calculus class. If you're in college, this would be like day 1. What you would start with is doing it backwards.
Calculus, and now it's
Anti-calculus, yes. Yes. All right, so let's see what we can do with that. That's why I had you practice those derivatives so that they would be fresh in your mind. Okay, so here we go. Here are regular functions, f, g, and h. So let's just quickly go through what f prime and g prime and h prime would be. Okay, so Leo, what's f prime?
Is 2x and x and the 2 in top and that's all.
Yeah, so x squared on the top. Anything else?
And
The 3 is in the front. Okay, so that's 3x squared. Okay, Nate, what's the derivative for g prime?
3x.
3x squared. Okay, and Christine? H prime?
3x squared.
All right, so these are called a family of functions. Okay, what's different about the functions? The original functions, what's different about them?
They have different numbers.
Okay, they have different constant values, but what's the same? They're all x cubed, right? So they all have their different plus values, different constants. Okay, we call these constants at the end. Okay, so there are different constants, but it's the same cubic. This is called a family of functions, where they're all cubic, but they have a different constant, but they all share the same derivatives. So when you work on antiderivatives and you go back, that becomes the question. If I'm going backwards, if I'm going from 3x squared back here, how do I know what constant is going to be there? Okay, because it could be any constant. It could be lots of different constants that would all belong to the same thing. Okay, we need to agree on some of our notation here. We learned in first semester that if you start with f of x being the function, then f prime of x is always the derivative. Okay, that's what we learned, that prime notation. Okay, that means derivative. If I want you to do an antiderivative, then I'm going to use a capital letter. Okay, so I'm going to use capital f of x if I want you to go the opposite direction. So if I use a prime, that means I want you to go in the derivative direction. If I use a capital, then I want you to go in the antiderivative direction. And with every time you do an antiderivative, you have to add what's called the constant on the end. And that constant, you just put a plus with a capital C. That capital C represents all of the different constants that the other functions could have. It could be a plus 5, it could be a minus 7, it could be whatever, but that's how we write it. And so let's remember how our rules go. When we have a function that is x and it has an n power, when we do a derivative, the rule was this. We moved the n power where? To the front. And then what happened to it after we moved it to the front? We subtracted 1, right? So that was the rule. Move n to the front, so multiply and then subtract. Okay, now let's think about anti-rules. I just said multiply and I said subtract. So what's the anti of multiplication? Division. What's the anti of subtraction? Addition. And I need you to reverse the order. Okay, so the order here is multiply, then subtract. I need you to reverse the order and the operation when you do an antiderivative. So let's see how that's going to work out. So it's going to have x. So what would come first? Add. Add. So it'll be n plus 1. Okay, you add instead of subtract. And then, what's the next operation? Divide. And you divide by n plus 1. Not just n, but you divide by the n plus 1 that you had. So it's add, then divide. So if it's multiply, then subtract, then an antiderivative is always add, then divide. Okay, so we're just going to practice that. So here we go. X cubed is the middle function. Let's do f prime first. F prime says multiply, then subtract. So that would be 3x, and then we subtract to get 2. When we do the antiderivative for capital, we're going to add first, then divide. So what would the power become? 4. And then what do I do with that power? I divide by 4. So the power is 4, and I divide by 4. And then you just have to remember to put plus capital C, which represents any constant that could be added to that family of antiderivatives. Okay, let's try another one. Okay, Kira, do the derivative. If to f to 5x to the 4th. 20x to the 3rd. Good. You want to do the antiderivative?
I'll try.
All right, so it'll be 5. We start with 5x. Okay, now what? 5x to the 5th divided by 5 plus c. And what happens to 5x to the 5th divided by 5?
Just becomes x to the 5th.
Exactly. And so the antiderivative is simply x to the 5th. And that's your final answer. See, these aren't so bad once you know how to do them. Okay, all right, Sydney, you try the next one. Let's do the derivative.
3 halves x to the 1/2.
Okay, 3/2 x, and then subtracting 1 just gives me 1/2. Okay, good. Now can you go the opposite direction? So x to the 5 halves, good. Not divided by 3 halves, divided by the same thing, the same power. Divided, yeah, it's got to be the same number. So x to the 5 halves divided by 5 halves. Now, more often than not, like with Kira's question, she got to reduce hers to clean it up. There's a way to clean this up too. We wouldn't want to leave 5 halves in our denominator because that's awkward. So instead of leaving 5 halves in the denominator, you're going to, what's the same operation as dividing by a fraction? Multiply by the reciprocal. So you would more often see this as a multiplication, and it would be by 2/5 out in the front. And then don't forget your plus capital C on the end. So you would write it like that. You don't have to change the powers into square roots or anything. As long as they're not negative, you can leave them the way they are. Okay, if they're negative, you do have to do it, but if they're not negative, you can leave it just the way they are. Okay. So let's try something a little different. Okay, down now at the very bottom, I have dy dx. So that tells me that's a derivative. Okay, I would want to think of this as x to the 1/2. Okay, so Jeffrey, if that's the derivative, what's the regular y? Where did that come? What do you think that was going to be?
It would be. It would be
Should the power be higher or lower?
higher.
Power should be higher. Okay, how much higher?
1.
Okay, so what should it be?
1 but times 1/2.
Let's write it. We don't write our powers that way.
X times square root of x.
No. I don't want you to write 1.5. Okay, that's not a good way to write a power.
2/3.
You're getting closer. 1 1/2 is 3/2. Okay? Now what should I do with that 3/2 now that I've made the power bigger? What do you always do when you make the power bigger? I divide by that power, so I would also divide by 3/2. You can't make the power bigger without dividing it by something, okay? But we also don't like to divide by 3/2. So instead, we would say, okay, we're going to do 2/3 to that, and then we have to add a constant C. Now I want you to go to capital Y, which means I want you to do it again. Okay, so now I'm going to capital Y. So now we're going to raise the power again. So I raise it, so 2/3 is still there, but I raise the 3/2 up again. That would be up now to 5/2. And then I have to multiply by that reciprocal. And that reciprocal is 2/5 plus. Now the letter constant C is there, but it has an antiderivative also. C is just a number. Remember that that is just a constant. And when you do an antiderivative to something that's just a plain constant, you attach a variable to it. Okay, so if it was like 5, it becomes 5x. But this has another constant added to it. Every time you do an antiderivative, you have another constant that comes into the question. So you bring another constant in. Maybe we can call this a constant D or something. You can use, I like to use capital letters for my constants. I usually use, a bold capital letter for my antiderivatives and regular ones. Okay, let's try another one. Okay, as long as you can make it a power, you can make the powers lower if you're going to a derivative. You can make it higher if you're going to an antiderivative. So 3 over x squared first should be rewritten 3x to the -2. Okay, that should be the first thing. Always make sure that your power is written in a way you can do it. Okay, so Nate, make the power lower to take a derivative.
It would be -6x
-6x to the -3. Very good. You just made the power lower. Good job. Okay, Sue, make the power bigger to find an antiderivative.
-3 over x.
Okay, can you do it with the powers so that we all understand?
Oh, so 3x power -1.
Okay, good.
Divided by -1.
Divided by -1. Okay, and then he's simplifying and cleaning that up. So that's where he's dividing by the negative, and he said, okay, so I'll put my negative out front, but you're forgetting the plus C. Okay, every time you forget a plus C, I have to take a half a point off, and it starts to add up on quizzes and tests when you forget that. Now, you wouldn't want to leave any of these answers as their final version because all of them have negatives. So you would want to fix all of them before you would write your final answer. So this would have a denominator of x cubed with a -6 on the top. This would have a denominator of x squared with a +3 on the top. And then the other one, I'm running out of space here, would have a denominator with an x and then a -3 on the top and then a plus C on the end. So it's fine to leave fractions in your answers, but it's not fine to leave negatives. Okay, any questions on these antiderivatives of making the powers bigger or smaller? This is how you do powers. But we also need to know how to do logs, and we also have to know how to do trig and inverse trig. That's why I had you review all of that last night. Oh, here's one more with power. Okay, 2 over x is 2x to the -1. Okay, Christine, make the power lower to find our derivative.
Negative 2x to the -2.
Okay, good job. All right, now make the power bigger to find the antiderivative.
2x to the 0 divided by 0
Plus?
plus c.
Okay. So she's done all the math correctly. She's lowered the power correctly, and she raised the power correctly. However, what problem do we run into? You're not allowed to divide things by 0. So she did it right. She made the power higher, and she divided by that value, the new power. The problem is that violates one of the rules of math. So this is a special case. This has a special antiderivative. So we mark this as a special case of dividing by 0. And if that ever happens, then it has a special antiderivative. So you don't want to use anything that would divide by 0. Instead, the antiderivative is a natural log. And the 2 goes in front, and the x goes in an absolute value like that. So the 2 is separate. We put the 2 out in front. Okay, so this is a special case. It only happens when you divide by 0. Sometimes even my AP students try and use natural log way too much, and they're not supposed to. They're only supposed to use it in the times where 0 would be division. You need a special rule for that. Okay, so we would do a similar thing here. 2 plus x should be understood as parentheses 2 plus x to the negative first. Now, if I want to lower that power, I can do that. But let's look at how this is all going to go. Look at the symbol that's used right here. That's a dy dx. Do you remember what the symbol is when you go lower than that? How we wrote that? D2, right. So we would write D2 to show that we were making it a derivative lower. So we can lower this. We lower it by pulling the negative 1 to the front and by lowering it to negative 2. So that makes it lower. If we want to make this higher, the dy dx that's circled in blue, if you want to make that higher, it just goes to plain lowercase y. Not uppercase yet. You don't change to uppercase until you take a regular y and you want to make it an uppercase y, but we're doing a lowercase y. And then here is a situation where 2 plus x, if I raise that to a 0 power and divide by 0, this is an example of a special case. So it is not 2 plus x to the 0 divided by 0, so we cross that out. Instead, it's a natural log. And the natural log doesn't have anything in front, not like last time. The last time it had a 2 out in front. This time the 2 is attached to the x by addition. So the 2 and the x both go inside the natural log. So this would be natural log absolute value of 2 plus x, but nothing out in front. And it's because both the 2 and the plus and the x are all in the parentheses. So whatever's in the parentheses is the part that goes in the absolute value. If it's not in the parentheses, it would go out in front. Okay, let's think about working on trig. Okay, so you reviewed from yesterday. What's the derivative of sine?
Negative. Cosine.
Negative or positive? Positive cosine. Okay. The antiderivative of sine is negative cosine plus c. Okay, the derivative is positive. The antiderivative is negative. So it's backwards from what it was before. Okay, before all the cos had negative derivatives. This time all the cos have positive derivatives. So sine has a negative derivative going that way. I usually make kind of a list. I know that sine turns into cosine. Cosine turns into negative sine. Negative sine turns into negative cosine. And then if I get to that, then I cycle back to the beginning and I start all over again. That's the order of how the trig derivatives go. So then I have to think about how the order of antiderivatives would go. So the antiderivatives are going to go the other way. And they all go and then around to finish. So if you know the order of how they go, you'll be able to go both in the derivative order in the antiderivative order. All right. If you're doing cosecant cotangent, you have to think, is this easier to do a derivative or is it easier to do an antiderivative from what you know about cosecant cotangent? Okay, it's easier to do an anti. Okay, because cosecant cotangent comes from something. It comes from the derivative of cotangent. Excuse me, it comes from the derivative of cosecant. So its antiderivative is negative cosecant plus c. That's how they're related. Don't know why that changed colors. If you're going to do the derivative, it's much harder. Yeah, the derivative would need the product rule, and that's going to take a long time. So we're not going to do that right now. But it's sometimes in trig, it's a lot easier to do the antiderivative. The antiderivative is simpler than the derivative. And again, it's going to really help if you know, maybe you want to make a note card or something that has all of the trig derivatives on it. If I were to do that, I would think about this. I'd think about sine turns to cosine, and cosine turns to sine, negative sine, I mean. So then I'd have to think about how I would go backwards. Okay, so that cosine in an anti would turn back into sine, and negative cosine would turn back into positive cosine. And I'd think about how tangent turns into secant squared. So then I'd have to think about how that would go backwards. And how cotangent turns into negative cosecant squared. So I'd have to think about how I did that backwards for an antiderivative. And the last one were secant and cosecant. And cosecant turns into a combination of secant tangent. Cosecant turns into the combination of negative cosecant cotangent. So that's why I was able to go backwards from that one back into cosecant. So if you know your relationships, it's a lot, you'll be able to recognize going backwards and forwards. All right, I'd maybe make a note card or keep that handy on my homework. Okay, so then here comes, yeah.
If you go back to that for 1 second.
You want to snag that? You can take a picture of it too if you want. But this is all in your notes from chapter 3. If you went back to your chapters, if you have them in Notability still, they're all still there. Got what you need? Okay. All right, so now we will need to look at exponential. If you know how to do the derivative, then you're going to be able to do the antiderivative. The derivative rule for 2 to the x is 2 to the x times ln 2. The rule is multiplication. You keep 2 to the x as itself, and exponential stays an exponential, but then you times it, and this is called the chain rule. So if something needs the chain rule in derivatives, it's going to need the anti-chain rule. That's okay. So the chain rule was always multiplying. What do you think the anti-chain rule is? Divide. So just ask yourself, how did I do the derivative? And then reverse it to do the antiderivative. So the antiderivative would be 2 to the x divided by ln 2. So if you know how to do it the front way, you could for sure do it the back way. E to the 5x. And say, how did I do the derivative of that again? The derivative was e to the 5x times ln e times chain rule 5. And that's all multiplication of chain rule. So you do the exact same thing backwards for the antiderivative. The antiderivative would be e to the 5x divided by ln e and 5. They're both division. They're both in the denominator. And then throw a plus c on there because you did an antiderivative. Of course, what's the ln of e? 1. So you would turn that into 1 in both cases. But always ask yourself, what did I do for my derivative? Okay.
Oh my gosh, this is 45 pages.
No, we're not doing them all today. We're not doing them all today. That's all of them. That's like today and next week and day. It's fine. Okay. Nate might recognize this. This was his question earlier today that we did notes on. 1 over 1 plus x squared. That's one of those inverse tan ones. Okay? So you're just going to have to recognize that one. Oh, it's positive on top. So that's antiderivative going to be inverse tan of x, and then throw a plus c on it. You would have to do the quotient rule to take the derivative, which we're not going to do today. Or ever. So you're going to have to, this is a special case again. You just have to know it, this one. You have to memorize it. Just like you memorize the derivative, you got to see it and then be able to do the antiderivative. If it was negative, it would be cotangent inverse. Negatives are always the co. All right, so here's how this is going to work. If you're given an f prime of two things, the antiderivative is plain f. And then we follow the rules. The antiderivative of 2x means I take 2x and I make its power bigger. And what should its new power be?
3.
Its power needs to just be 2. I'm just going up by 1. But what do I do with that? Divide. Okay, then plus cosecant squared works backwards into, do you remember what term that is?
Negative.
Negative cotangent. And then because these were both antiderivatives, what do I throw on the end? Plus c, and then the answer is done. If you know your antiderivatives, your homework will go fast. What should I do with the two 2's at the beginning? Reduce them away, okay? All right, let's try another one. This one is dy dx. So the antiderivative of dy dx is plain y. All right, what's the antiderivative of 3x squared? Well, it's 3x, and I have to make the power what new power? Bigger to what? A 3. What do I do with the new 3? Divide. And then what is the antiderivative of cosine?
Negative.
That's the derivative of cosine. What's the antiderivative? Positive sine. And then what do I throw on the end? Plus c. See, you're getting it. And that's the answer. X cubed plus sine plus c. How do you check your work?
You don't.
Plug it.
Now plug it in. Find the derivative and see if you end up with what you started with, because it should match. There should be a perfect match. Did I have anything else? Oh, I know. You do plug something in, Jeffrey. Sometimes you get two numbers to plug in like this. You get a 0 and a 1. So you plug in 0 for all the x's and 1 for y, and that helps you to figure out what c is. So sometimes you can do that. That would be the plug-in part. I was going to do one of those with you, but we ran out. That was our last one. All right, have a great weekend, everybody. Don't forget the taco truck will be here in about a half an hour. And if you're at Broadway, good luck with your dress rehearsal tonight.